outside. Okay, this we will do in the middle of the lecture or at the end of the lecture, okay? I really wanted to which kind of conference is outside door here? Okay. I have 4 hours with you master gig, and before I do that, I must introduce myself. I will see you first time. Not long time at Acetylcholine University either. So, So my name is, as you can read here, my name is Untitled Chapter. I'm chair of the Department of Physiology at Untitled University. I have my degrees MD and PhD in Physiology from Ruhr University, Bochum in Germany, long ago. And then I worked almost 22 years at the Ruhr University, Bochum. And then I was at the University of California, San Diego, and then to Western Reserve University in Cleveland, Ohio, and then 14 years at Ross University School of Medicine, which is also an American Caribbean. And last December, I joined Basel University. So that is enough about me. And that is how can you approach me if you have questions. My office is located in the 3rd floor, and the room number is S349. And I have office hours from noon to 2 p.m., but you can drop off anytime you want. You can come. We have an open door policy as it is convenient to you. You can come there and ask your questions. Also, certainly I'm for you there to answer your emails. Here, there's one with this link to the pretest doesn't work actually. In the past, it was a free in the internet. That is a series of question books for all disciplines, and also one in physiology, but now it should be purchased. Therefore, the link doesn't work anymore. I'm sorry for that, but I will post you some training questions in the days which coming. They are not posted yet. And debate my philosophy because I think first you learn and then go with some questions. If you just put up time and start to solve questions, then we don't understand the next time that you solve them is useless because you have seen them already. Yes. Therefore, after you have the lectures, then do these questions to be prepared. Okay, these are the learning objectives for our today. I don't want objectives. I will cover all of these learning objectives we see in the course of the lecture. And then we have three different types of the muscle. As you know, skeletal muscle, hard muscle, and smooth muscle. In this semester, we deal with the physiology of the skeletal muscle and smooth muscle. In next semester, we will learn the hard muscle, because that is next semester, the cardiovascular block. And the point is that the skeletal muscle, today I want to start with the skeletal muscle. The skeletal part, contraction of the muscle, produce force. First, the muscle requires an action potential, an excitation that we call an action potential. Without action potential in the skeletal muscle, there will be no contraction. And the skeletal muscle is not capable of producing its own action potential. Okay? It cannot generate its own action potential from the beginning. Therefore, an action potential transmitted to a nerve ending which comes close to the surface of the muscle, an action potential propagated over the nerve ending. This action potential is transmitted to the muscle. And that is what we call neuromuscular transmission, neuromuscular signal transmission. And that is what we learn today. You see here is a nerve, and the axon of the nerve, as it approaches or comes close to the surface of the muscle, it divides to different branches, little branches, little processes. And each of these processes come close to the surface of the muscle, but it doesn't touch the surface. It is not directly connected to the muscle. There is always a gap between the muscle and the nerve ending. And you see this for me. That is the nerve ending. And here, this membrane, we call it presynaptic membrane, also the nerve terminal membrane. And just below that, on the muscle surface, this muscle membrane gets a specific property. This membrane is called implant, okay? Or postsynaptic membrane. That is called also implant. And all these membranes are separated by a cleft, which is called synaptic cleft. And all these three structures together, presynaptic membrane, implant, and the cleft together in a neuromuscular junction. Okay, that is so much about anatomy. Now we want to see how action potential is transmitted from nerve to the muscle. If you look at this nerve ending here, and you see this chart across the membrane, what do you think? It is an action potential or a resting potential? From you have learned from Dr. Shawal. Why it is an action potential? Yes, but I don't know if you look at the picture, how do you know that that is an action potential? That is correct. The inside of the membrane, as you see here, is positively charged. You know that the action potential, the inside is positive, outside negative. If it were a resting potential, it would be the opposite. So if you look at the picture, you know an action potential is propagated over this membrane. And now this action potential, which depolarizes this membrane, opens these calcium channels. These are voltage-gated calcium channels. As the channel opens, then the calcium is moving from outside into the cell. Why it is moving from outside into the cell and not from inside to the out? Correct. Very good. That the calcium concentration outside is 10,000 times more than the concentration inside the cell. Therefore, then the driving force, it brings the calcium from outside into the cell. And this increase in calcium concentration in these nerve endings causes the fusion of these vesicles with the membrane. And that is causes the release of a transmitter there. And this transmitter is called acetylcholine. All these vesicles are filled with acetylcholine. And acetylcholine is then released in the cleft and diffused to the other side, to the muscle side. On the end plate, you have acetylcholine receptors. And these receptors are at the same time channels, ion channels. Each receptor binds to acetylcholine molecules and then opens it. If the channel is closed, nothing can move through. But if after binding with acetylcholine, the channel opens, and this channel is a cation channel. It means it let all positive charges to go through. It is not only sodium, it is also potassium. Both of them can move through this channel. But we will discuss it later on, but mostly it is sodium which goes through. Sodium moves from outside of the cell into the cell. This mouse is make me crazy. It's not so good mouse. Sodium moves from the outside into the muscle cell and depolarizes the muscle membrane. So from what you have learned, it is an action, a potential, or it is another type of potential. Graded potential, because they are not voltage-gated sodium channels. They are ligand-gated sodium channels or cation channels, and that produces a graded potential. And now this graded potential propagates to the sides, to this side, and also to that side. And as it propagates, what happens? It takes amplitude. This graded potential propagates the lumps of matter. Therefore, as this potential reaches this part of the membrane, its amplitude is a little bit smaller. And now, this part of the membrane, you have voltage-gated sodium channels. And now, if this graded potential, which reaches that area, is large enough to reach the threshold potential, then it can open the voltage-gated sodium channels and produce an action potential at this location. And then this action potential propagates over the entire membrane of the muscle fiber. First, you have a graded potential which propagates and opens the voltage-gated sodium channel, and then an action potential is produced, propagate over the membrane of the muscle. Okay? So, if you look at this picture, those are in the cytoplasm here somewhere. And to fuse with the membrane, they must become enclosed with the viscosity of the membrane. Have you ever been by a boat in the river or cannot just jump from the ball to the land. The ball must come close to the land, dock, and then the door becomes open, can come out. That is the same process here. These vesicles are like bolts. They must be brought close to the membrane and will be docked here, the membrane, and then it opens. It means that this vesicle, which docks at the membrane, must be prepared to release its content. And the process of preparing for the release of content is called priming. The vesicle is docked and must be primed before it can fuse, its membrane can fuse with the perisynaptic membrane. Okay, docking and priming. And now we want how it happens. Normally, this docking and priming is not happening overall in the muscle. Overall here, it happens only in certain areas of this synaptic membrane, and those areas are called active zones. It means that vesicles are not at the active zone, or release zone, people call it. Okay, and we want to look how this docking and priming happens. Now what you see, that is the vesicle, and that is the vesical membrane, that is the perisynaptic membrane. Okay? The muscle membrane is not shown here. Only the perisynaptic membrane, nerve terminals, and that is membrane. This membrane of the vesicle, we have a protein which is called Acetylcholine Binds. And also we have two other proteins. One is called suntaxin, and the other is called SNAP 25. Also, these two proteins of the perisynaptic membrane is connected to the synaptic protein of the vesicle. And then you can see this vesicle is docked, this membrane. And all these three molecules together is called core complex. Core complex. So by the core complex, the vesicle is docked at the perisynaptic membrane. Then this one, you mean? Okay. Okay. Now what you see here, this core complex, this vesicle is connected to the perisynaptic membrane, but still the membranes cannot fuse together. The fusion is inhibited by another protein which is called synaptotacmin. And after this docking, this vesicle will be prepared for release of acetylcholine, which is called priming. And for the priming, you need energy. And energy comes from hydrolyzation of ATP. And the protein, the ATPase, which does it, is called NSF. That is all written in the text below the pictures. You have them, all the information. Therefore, after this is energized, then this vesicle is primed to release its content. But still, it cannot fuse with the membrane at the neuromuscular junction. somewhere else you see in physiology that after vesicle is primed, it fuses directly with the membrane and releases content. Here, it doesn't happen. And this fusion is inhibited by synaptotacmine until calcium enters this space and bind with synaptotacmine. Then this braking function is released, and then the vesicle can fuse. Also, everything is prepared until an action potential arrives. After action potential arrives here, then opens this calcium channel, and now calcium comes into the cell here, into the nerve ending, binds with synaptotacmine. Synaptotacmine had two binding sites for calcium. And after the calcium binds, then the fusion of these two membranes is occurring, and the acetylcholine content of this vesicle will be released in synaptic cleft. Okay? So action potential is needed for that purpose. Now we want to see what happens with acetylcholine after it is released. Now acetylcholine diffuses to the muscle side, and on the muscle membrane, on the postsynaptic membrane, there are channels, acetylcholine channels, which are closed if there is no acetylcholine to bind with the channel. After acetylcholine arrives here, each channel or each receptor binds to acetylcholine molecules, and now this cation channel is opening. As I told you before, now sodium can go into the cell and potassium can go out of the cell. And now this opening increases the permeability of this channel to the same extent for sodium and potassium. The question is now, if one sodium is coming in and one potassium goes out, nothing happens with the membrane potential. No depolarization. And now the questions for you is, which of these ions diffuse more through this channel? Sodium. Why do you think sodium does it? That is absolutely correct. You must consider two factors. One is the driving force for these ions. And the driving force, as you have learned, was always the difference between equilibrium potential and resting potential. For sodium, the difference is between 70 to 60 millivolt is about 130 millivolt. 130 millimole difference is the driving force for sodium to bring it in. For potassium, the equilibrium potential is 90 millivolt, the membrane potential minus 70, minus 90, minus 70, the difference is only 20 millivolt. So the driving force for potassium is much less than driving force for sodium. And as you know, during resting condition, the sodium-potassium permeability, the ratio of the two, is very low. It means that if you take the permeability for sodium 1, the permeability for potassium is probably 100. And now if it increases, opening of the channel increases the permeability for both to the same extent, let's say by 10, you had the permeability 1 for sodium. And now you get the permeability 10. It is a 10-fold increase in permeability. But if you look at the permeability for potassium was 100, and you increase by 10, it is 110. You get a 10% increase in permeability. So also the permeability increase are in absolute term equal. The relative contribution of permeability increase for sodium is much, much larger than potassium. Therefore, sodium can go diffuse better through this channel. Because of these two factors, more sodium comes in as potassium goes out. And that causes this membrane to depolarize. Okay? Then you have a depolarization, a graded potential, which propagates further. And you see here you produce a graded potential, propagate to the sides. And now at these sides, you have a high density of voltage-gated sodium channels. And if this potential reach the threshold, opens the sodium channels and action potential is produced. Okay? And you see, like these waves, the action potential is produced and propagate over the entire membrane of the muscle. Okay, this is a slide which shows you the membrane voltage against time. You see, if this graded potential, that is the threshold potential, if the graded potential is larger than threshold, then it produces an action potential. If graded potential, like here, is less than threshold potential, this potential will die, cannot produce an action potential. Now the question is, what decides if this potential is large or not large? How it comes that we have different potentials with different amplitude. Some of them cannot reach the threshold and disappear. They are called miniature end-plate potential. Miniature, it means they are very small. And some others reach and produce action potential. We want to understand that. And that is what you understand by the release of acetylcholine. You see here that acetylcholine is not released as a one molecule. It is released into the cleft and come and find its receptor. The whole package here is released. That package, the content of one vesicle, is called a quantum, a package. And acetylcholine molecules are released in multiple quantum. Each one is a quantum. And each quantum here contains 10,000 acetylcholine molecules. 10,000 acetylcholine molecules. After this vesicle fused with the membrane, all 10,000s are released. It is not that it released 300 or 400 or 100. It is either 10,000 or 0. Okay, the whole quant will be released. And now this quant, if it is one of those, and binds with acetylcholine receptors here, it produces a smaller amplitude of depolarization in postsynaptic membrane. You have learned that graded potential can sum. Action potential is all or none, but graded potential can show a summation. Therefore, if one is released, then produce, let's say, 1 millivolt depolarization. If SY are released, then it produces SY millivolt depolarization, dry millivolt depolarization. One is important. The smallest units of depolarization, which is produced by one of these, is cannot be broken down to smaller ones. Let's say if the content here produce 1 millimolt depolarization, if you have multiple content, it is 1, 2, 3, 4, 5 millimolt depolarization. It is never 1.5, 2.5, 4.8. That is not the case. It is a multiple of the smallest unit. And that has been experimentally found by Katz, who got the Nobel Prize for this work. And now this, normally, if there is no action potential, some of these vesicles are fusing with the membrane and release their content. And they produce a small depolarization here, which is the miniature in-plate potential, which cannot elicit an action potential, okay? A spontaneous release of these. And if action potential arrives here, one single action potential in average causes the fusion of 100 vesicles. One action potential, 100 vesicles, every vesicle 10,000 molecules, it makes 1 million molecules of acetylcholine, which are released in the synaptic cleft. And that produces a significant depolarization of the membrane that as it diffuses further and the amplitude reduces, still it is large enough to reach the threshold and produce an action potential, okay? So in this slide, what you see is a summary. Acetylcholine binds with the receptor. Receptor is a cation channel, and that is opening. You get sodium influx, potassium efflux, and as a whole, you get a depolarization of the membrane, a graded potential. And that one opens voltage-gated sodium channels, which produce sodium influx that produce a large depolarization, which is called action potential, And you see here, that is the acetylcholine channel or receptor channel. And this one is the voltage-gated sodium channel. You produce a graded potential here, and that opens and these channels produce an action potential there. And now the action potential propagates over the entire muscle surface. So, and that is again, you see, the muscle cannot produce its own action potential. The action potential comes from the axon of the nerve, and it releases acetylcholine, produce a graded potential, and then an action potential. And this muscle action potential is the one which causes the contraction. And where are these active zones and these acetylcholine receptors which are producing graded potential? They are in the muscle fibers, mostly located in the middle of the nerve, of the muscle fiber. Do you remember by the nerve, the action potential was first produced at one end of the axon and propagate towards the other end. And that end was the helix of the nerve. In the muscle, it is different. It is produced first in the middle of the nerve fibers, and from there it is spread over the entire surface. So, and now I want to talk about how the whole process of the acetylcholine release can be recycled. First, we talk about recycling of the vesicle membrane, the membrane itself without acetylcholine. And then we talk about the recycling of acetylcholine. So here you see that is a vesicle filled with acetylcholine. After it fused with the membrane of the vesicle will be incorporated into this presynaptic membrane. It becomes part of the presynaptic membrane. Then you can imagine if nothing happens, then the next vesicle fuse with the membrane and become part of the membrane, the next one. And this membrane, presynaptic membrane, become larger and larger and larger and larger. And it is not possible. Therefore, this membrane, which is incorporated into the presynaptic membrane, must be retrieved back and form a new vesicle membrane. And that is what is happening here. This membrane is recognized by a molecule which is called calatrine. Calatrine pinch off this membrane from the surface and cover this membrane. That is a calatrine coat, this white one. And the whole thing, we call it a coated PID. Okay? The coat is calatrine. And then it's separate from the membrane and produce a coated vesicle. And then the calatrine, a part of this vesicle will be disassembled, will be separated from the vesicle. And the vesicles, this vesicle without calatrine, they fuse together and build an endosome. And from this endosome, new vesicles will be produced, new vesicles. And then after the vesicles are formed, they are filled with acetylcholine. And in the membrane of this vesicle, there are transporter, which transport acetylcholine into the vesicle and build inside a very high concentration. That is an active transport of acetylcholine from outside, also from cytoplasm into the vesicle. That is the recycling process of the vesicle itself. And now we want to see in detail what happens with these recycling. You see here is calatrine molecule. Calatrine has two parts. One is called adaptine, and the other part is triskelion. This red part is called triskelion. Adaptine, the vesicle membrane, which was incorporated into the perisynaptic membrane, has receptors. And these receptors are recognized by adaptine. Adaptine binds with these receptors. And now the form of this calatrine, you see, it is like this, causes that the membrane pinch off from the surface, okay? Because of the form of the triskelion. And after you coated pad, after you have this vesicle in this form, it will be separated from the membrane. For this separation, it requires energy. And energy is coming from GTP, not from ATP, from GTP. And protein, which hydrolyzes GTP, is called dynamine or dunamine. And that protein, hydrolyzed GTP, get the energy and use that energy to separate this vesicle from the membrane. Although the separation is happening with the help of dunamine, another protein, which is a GTPase, protein which hydrolyzes GTP for delivery of energy. And now you get a coated vesicle. And the calatrine of this vesicle will be separated from the vesicle, and it again requires energy. And this energy comes from ATP, not from GTP, but from ATP. And the protein which does it is an ATPase. Okay? Hydrolyzing of ATP delivers the energy to separate or disassemble this calatrine coat. And now the vesicle is without coat and fused together to endosome. So, that was the recycling of the vesicle membrane. And now we look at the recycling from acetylcholine itself. Here, after acetylcholine binds with the receptor, at this membrane, you have an enzyme which is called acetylcholine esterase. It degrade the acetylcholine. acetylcholine will be metabolized by this enzyme. Also, the enzyme is called acetylcholine esterase. That is located at the postsynaptic membrane of this muscle. And as soon as acetylcholine binds with the receptor, after a short time, it is degraded by acetylcholine esterase. It doesn't stay there at the receptor for a long time. And now it is degraded to choline in another part. This choline part is transported back into the nerve terminal with the help of the transporters here at the perisynaptic membrane. Okay, the choline is transported into the nerve terminal. And now in the nerve terminal, you have acetylcoenzyme A, acetylcoenzyme A, and that one and choline are combined together with the help of this enzyme, which is choline acetyltransferase, and produce acetylcholine. And this acetylcholine will be then used to fill up the empty vesicles. Also, the choline part is recycled. Okay? And now we have a new form vesicle, and they are ready until the next action potential to be released in the cleft. So, now if you look at this neuromuscular transmission, you see immediately that there are a lot of possibilities to block this transmission. So, if you look at this picture, you see that you have a lot of possibilities to block the neuromuscular transmission. They are shown here. First, for example, if you block the potassium channel, then the resting membrane potential dies and nothing will be, this nerve is not functioning anymore. And so, the dendrotoxin can block also the potassium channel here. Another possibility, and also dendrotoxin blocks sodium channels. If you block sodium channel, you cannot produce an action potential in the nerve. And another possibility to block is here the possibility 3, which are the toxins. I must say, for you to remember better, this neuromuscular transmission can be blocked by 3 different processes. One of those are toxins, which blocks the channels or other things. These toxins are produced by the bacteria, or they are produced by the animals. And then the other possibility is that we produce drugs as physician. We produce drugs to block the neuromuscular transmission. That is necessary, for example, during operations. You want to block the neuromuscular transmission that you don't have any muscle contraction. Otherwise, you don't know where the knife will end, the knife of a surgeon. And the third possibility is the diseases. There are diseases which interfere with this neuromuscular transmission. If I start first with the diseases, at least 2. One is called Mustania Gravis. By Mustania Gravis, the patient has, it is an autoimmune disease. The patient has antibody against acetylcholine receptors. My God, there is one mistake and then bring everything out. antibodies against acetylcholine receptors. Therefore, it interferes with the neuromuscular transmission, and you get weakness of the muscle. Another disease is Lambert-Eaton syndrome. By Lambert-Eaton, there are again anticorpor, that is an autoimmune disease, against calcium channels, and then blocks the neuromuscular transmission, or at least weaken the neuromuscular transmission. And then you have these toxins from animals. For instance, botulinum toxin. Botulinum toxin enters these nerve terminals and cleave the proteins of core complex. The proteins of core complex, those three, synaptobravin, xantaxin, and SNRP25, those proteins will be destroyed. And therefore, the fusion of the vesicle with the membrane is not happening. Block the neuromuscular transmission, and also there are, for example, tetrodotoxin, which block the sodium channels or potassium channels, and then you cannot have a neuromuscular transmission. Important is for you these two groups. One is the group 4, that is acetylcholine antagonists. For instance, tubercularine. It binds with the acetylcholine receptor, but cannot open the channel. As a physician, you administer it. It goes bind with that acetylcholine. The channel will not be open, and now the acetylcholine, which is released, don't find any empty receptor to bind with. The effect is competitive. If you have a lot of acetylcholine, can push the tubercularine out and bind there. So that is a possibility to block neuromuscular transmission. Another possibility is to use the acetylcholine agonist, not antagonist, agonist, the molecules which are like acetylcholine. One of them is succinylcholine. If you apply succinylcholine, binds with the acetylcholine receptor, open the receptor. Then you would say why it cannot produce a graded potential. It can produce, if it opens the channel, then like acetylcholine, it can produce a graded potential. It does. It does produce a graded potential. And now the difference to acetylcholine is that succinylcholine cannot be destroyed by cholinesterase. Once it binds with the receptor, it remains there, and the receptor remains open for a long period of time. And if it is for a long period of time, then this depolarization is long-lasting depolarization. And this again, I did the same. I do it tomorrow. The next. Now I want to have the attendance.